Okay, thank you for being here. It's been a double 15 minutes break, so let's do it more efficiently the next time. So please, let's stick to the program because we have a really rich one. And now we'll start the Pitch Me Up sessions. For those of you that weren't there in Heraklion last year, I just want to remind you the principle. These are selected talks, short ones from the community. We have received something like around 30 abstracts for representation. We have selected around 12 of them. It's been selected by a selection committee between the ETP and Expo and also our Spanish partners. So I'm really glad that we have many speakers this year again. Let's say that the Pitch Me Up session it's just not, let's say, yet another short talk. It's been inspired also by the TAB experts. We had discussion on the way people should present their technology. And normally we said, okay, the classical pitch from a small company or an academic is too often just speaking about technology 90% of the time and then acknowledgements. And we want to, let's say, to encourage people to explain their mission, to explain their vision, to explain also in which sense their technology or the way they use is unique. So this is why we have prepared a single template that most of the speakers have really nicely respected. I will ask the speaker to stick to 8 to 10 minute talk. 8 minutes we can have question, 10 minutes we cannot have question. So we will start by a session about regenerative medicine and medical devices. And I'm really glad to welcome the first speakers, which is Fernando Herranz from Cybervivian.
Okay, thank you. Thanks for the opportunity of showing you today this project that we have titled Core Dope Nanoradio Tracers, Enhanced Molecular Imaging with Pulmonary and Cardiovascular Applications. So our vision is the combination of nanotechnology and radiochemistry because we think it can really change the way preclinical and clinical molecular imaging can be performed. There are many features that can be highlighted of this combination. For example, the possibility of having a proof with a radio tracer with site-dependent properties, including in a nanoparticle the sensitivity of nuclear imaging, or the easily tune the pharmacokinetics of a radio tracer that with traditional radiochemistry is not easy to do. So basically you have two options to attach a radioisotope to a nanoparticle, use a chelator and attach the radioisotope on the surface, or core dope the nanoparticle with the radioisotope. With the title of my talk, you can guess that we prefer this option where we integrate the radioisotope in the core of iron oxide nanoparticles. We prefer it because it's much faster, because we get much larger specific activities. We do this, as you will see now, in just one step, rather than with several functionalization and purification steps that you need to do with this approach. We have the radioisotope for PET signal, and then we have iron oxide nanoparticles. So we could do PET T2 MRI or PET T1 MRI. We much prefer the T1 MRI because we are focusing on atherosclerosis, and for atherosclerosis, having this really negative contrast typical of iron oxide nanoparticles is normally not the best tool. We prefer to synthesize these nanoparticles so small that they are more paramagnetic than superparamagnetic, so they provide a positive contrast. This is an example of my group with T2 MRI. This is the plug, and I really have to tell you where the signal is. We don't want that. We want to develop a tool that physicians can easily see where the signal is, because if you have to start looking for this signal at a clinical level, probably is not the most useful approach. So regarding the medical issue we are trying to address, in general, is the early diagnosis of diseases with hybrid molecular imaging. Particularly, we are focusing atherosclerosis. The typical, as you know, atherosclerosis is a wall thickening of main arteries that you can have two scenarios. One where many collagen and different proteins and calcium build a scaffold that stabilize the plaque. There is no clinical event. You will not notice that you have atherosclerosis. Or the problematic one where you have a rupture in the plaque, a thrombi is generated, and depending on where it happens, you can have myocardial infarction, ictus, etc. Currently, there are not really good tools for the unambiguous detection of these stages, where the plaque is starting to develop, where you already have time to change the course of the disease. This is where we want to focus, in these early stages of the disease. So our solution, we synthesize, as I mentioned before, these gallium-68 iron oxide core dope nanoparticles. very small one, we are around 3 nanometers in core size, with a very thick organic layer of around 10 nanometers. In one single step, by a microwave irradiation, in 10 minutes, we mix the coating agent, whatever we want. We have done this with polymers, small molecules, the iron chloride precursor, and gallium-68 from the elution of a generator. We obtain these nanoparticles. We purify them by different means, mainly by gas exclusion chromatography. This is the radioactive signal due to the nanoparticle, and this due to the small gallium, the small amount of gallium that has not been incorporated. We characterize that, in fact, the gallium is in the core, in the crystal structure of iron oxide nanoparticles by different techniques. For example, here, X-ray fluorescence or EDX nicely agree on the percentage of iron and gallium in the nanoparticles. Another advantage of this method is the reproducibility. This is the hydrodynamic size for 4 different syntheses of the nanoparticles, all exactly the same hydrodynamic size. We characterize the relaxivity because they are so small. They are more paramagnetic than superparamagnetic. They show a very large R1 value of 6.5 and a small R2 value of 20-something. You can see that in a phantom. The higher the amount of iron, the brighter is the signal in MRI, and the larger is the signal in the PET. So why our solution is unique? I think because of the type of technology we have developed, because of the features it presents. Just to mention some of them, they show a large specific activity, very large R1 value, large hydrophilic coating that helps you functionalize then even with the very, very hydrophobic peptides, as I will show you now. They are tunable in size, so you can have different properties, and they have a very large specific surface. We have been applying this in the last couple of years for different applications. First of all, if you have the nanoparticles just with the coating without any particular functionalization, because they are so small, they circulate for quite long in circulation. This is in a rabbit. This is the baseline magnetic resonance angiography. Once you inject the nanoparticles, you have the PET signal. You can clearly see the heart, the aorta, carotids. And once the radioisotope has decayed, you can take the same animal to MRI, and you can see a nice angiography of the animal with even the smallest vessels are visible. You can functionalize then with a different coating and adding a peptide. In this case was to detect angiogenesis. This is what I mentioned before. Here I don't have to tell you where you have to look to see the signal. You have a very small signal in the liver and a quite large and easy to identify signal in the tumor. But you can see also with positive contrast. This is the baseline of the tumor with no signal, and I think you can see here surrounding the tumor a positive signal, a positive contrast due to the accumulation of these nanoparticles. The most recent approach, we have functionalized nanoparticles with extremely hydrophobic peptide that is specific to neutrophils, and we have used it in a inflammation model in the lungs. If you use a control mice and inject the nanoparticles, only signal in the liver, there is no signal in the lungs. When you use the nanoparticle functionalized, a quite large signal in PET in the lungs. If now you do the same experiment, but with depletion of neutrophils, the signal in the lungs disappear. This is the heart. There is no signal in the lungs because there are no neutrophils there. This is the percentage of in vivo labeled neutrophils. Up to 50% of neutrophils in the lung has been labeled with the nanoparticle. And in a different experiments, if instead of neutrophil depletion, you perform macrophage depletion, the signal restores. So the nanoparticles accumulate in the lung. These nanoparticles, because the peptide and the size they have, they are targeting neutrophils, but not macrophages in this inflammation model. We just published this. Proof of concept. We want to use this platform for atherosclerosis. That is our main topic. So what we want, as I told you before, is an ambiguous detection of atherosclerosis, not the typical signal that you really need to fight for finding it. This is the PET ex vivo aorta of one ApoE, these mice that spontaneously generate atherosclerosis. You can clearly see accumulation of the particles in the aortic arch and renal bifurcations. That is normally where you have most of the plaque. You can do this in vivo. Here you can see, I think, the signal here, typical signal of an atherosclerosis developing at the at the aortic arch position. In a control mice without atherosclerosis, the same position, there is no signal. In mice with atherosclerosis but without the functionalization, there is no signal. So we are confident that we are getting what we wanted, at least at these initial steps. So next steps, testing more nanoradio tracers. We have a library of tracers that we want to test for this atherosclerosis. We have to finish the work with these ApoA mice that I just showed you. And then we want to move to rabbits because they show a atherosclerosis that is closer to the ones showed in humans. We need to perform toxicity studies. That is something an expertise that we don't have. So we want to collaborate with somebody with this nanotoxicity expertise. And what we are looking for, collaborations and funding, like everybody else. So thanks for your attention, and thanks to the nanomedicine group at CENIC, all technical units, and funding programs. And this is my contact details in case you need something. Thank you.
Thank you very much, Fernando.